second part to ionic equilibrium. Okay, we have done the first section of the acids and bases, and now we come to the second section on solubility equilibrium. Okay? Now, basically, when we talk about some of you really need a lesson in body language. I've often noticed that sometimes when I scold people, they don't get it because I'm assuming that they have a higher level of maturity than they actually do. So usually when I scold year 5, year 6, my assumption is that they are young adults destined for university. In recent years, right, I have been proven wrong many times. But I still persist in treating them like young adults. Are we ready to begin? Okay. Now, why is this topic important? The thing is, it has very many practical uses. From everything from mining, okay, on extraction of industrial materials, to medication. Okay. So, for example, one medical imaging, right, is to give you a suspension of barium sulfate before taking an X-ray. Now, X-rays usually pass through soft tissue. Okay? So they are good for taking images of things like bones, your skull, okay? And other hard substances. However, let's say if you want to take an image of, let's say, maybe your stomach or something like that, there is nothing to stop the X-ray from just going through and therefore not producing any image. So this is why they may give you, make you drink something that contains. My temper is quite short, and the thing for the 3 of you, I can take it out of you for the rest of the year. Okay, so you will drink something like barium sulfate. Barium is quite heavy metal. Okay, so that it will be absorbed. Now, barium sulfate is basically insoluble. Okay, so it will coat the inside of the intestinal tract, and therefore it will appear the X-ray as white, and therefore you see greater detail than a traditional X-ray. Now, you have to use an insoluble salt. because barium is toxic. If I were to give you barium nitrate to drink, okay, you would definitely be sent to the emergency room, but I think that maybe they cannot do very much for you. Because barium, if it's in barium nitrate, if you absorb it to your body, you will just die. Okay, so the barium sulfate, the fact that it's insoluble is important. Okay? Another thing where you would need to learn about this solubility equilibrium is in the formation of kidney stones. Okay? Now, some of you maybe your parents or your grandparents have had this, or maybe if you have suffered from a medical condition, you may also have this. Kidney stones have been said, the pain that you experience is more painful than giving birth. So someone wrote that on the internet forum, and a lot of people came in and said, how dare you say that? Nothing is more painful than giving birth. Then this lady came in, wrote, I have given birth. Kidney stones are more painful than giving birth. The pain is excruciating. I have had kidney stones before, and I remember just lying on the floor of I was in university at the time, so I was just lying on the floor of the hostel, unable to move. Okay? And the way that you have to get rid of it is either you have to drink lots and lots of water to dissolve it, or there will be other medications to help you dissolve it. Okay? Often, for males, when the kidney stone comes out, it will involve a lot of blood in your urine. I presume I do not have to elaborate on the anatomy, and therefore you can imagine how it comes out. Can you imagine now? 5M looks a bit blur. Afterwards, I will show you pictures. Okay? Now, kidney stones can be smooth, they can be jagged, and come in the shape of a star. Okay, which can be particularly painful to eliminate. Okay? They try not to do surgery now, but they use things like ultrasound to break up the stone, but it will produce very sharp-edged fragments, which also will trigger a lot of pain. Okay? So, you recognize the anion? You have dealt with it in the lab. This is the hot titration one. You titrate KMNO4. Nonetheless, needless to say, titrating with KMNO4 is not a way of getting out your kidney stone, okay? You cannot go and put KMNO4 into your kidney. Okay, so basically, the thing about not drinking enough water, possible, but there are other medical conditions that lead to this. Okay, so one of these is actually there can be sometimes a change in the pH of the fluid inside your kidney, and then it causes this to be precipitated out. Okay? So, that is the equilibrium. So, calcium ethane diuate, or in medical books, often they will use the older term calcium oxalate. Okay? So, you can get those crystals being precipitated out. So, there are many forms of kidney stones. Some are actually triggered by bacteria, and then it will form a nucleus, and then other salts will precipitate out. Yeah. Okay. So, there's an example of tooth decay. Okay, so the calcium phosphate with the OH group in there okay, is more soluble, and sometimes that's why they put fluoride in drinking water, because then the OH ion is replaced with the fluoride ion, and which is less soluble, and therefore it will make it harder. And that's okay. So it prevents tooth decay. However, if you put too much fluoride in there, then it may trigger other forms of decay. Okay, so there needs to be a balance. Alright, so we need to know about solubility and what we will call solubility product. Okay, how do you control the precipitation or the dissolution? What's the common ion effect? What's selective precipitation, complex ion formation, and the pH. Okay? So, solubility, basically the maximum amount or mass of a substance that will dissolve in a given volume of solvent at a specified temperature. So basically, it is the concentration of the solute in a saturated solution. Okay, so it can be expressed in mole per dm cube, gram per dm cube, and sometimes it's gram per 100 gram of solvent. Okay, the last one, you may think why would they use that, but let's say if industrially, right, it may be a better way of measuring, or more convenient way, because it's easier to find the mass of something than sometimes find the volume. Okay? It's easier to measure mass. And the thing with mass is it doesn't change with temperature, if you understand that. Okay, so let's say, try to visualize this. You will have a salt, you put it in water, okay? It starts to dissolve. Alright, so you have the barium and the sulfate. Okay, however, just as the ions leave the crystal, you can get ions returning. So eventually, there will be an equilibrium. Okay, a dynamic equilibrium. Okay? So, if you have a salt, when it dissolves, it will give you Na, N plus Nb, M minus. Okay? You can write equilibrium constant. Okay, so it's A to the power of M, B to the power of N over the A, B solid. Now, the thing is, for solids, the concentration is constant. Okay? So, you can rearrange this and you get a new constant, and you will call that the KSP. Okay? The units will depend on how many ions there are. Okay? Now, the important thing about KSP, it refers specifically to the concentration of ions in a saturated solution when the system is in equilibrium. Alright? I want you to bear this in mind, because later on we'll be talking about something called the ionic product, and it will look very similar to this. However, for that case, it is not in equilibrium, and it is not in a saturated solution. So this thing about KSP is important. It must be in equilibrium, and it is for a saturated solution. Okay? Okay, so for example, lead chloride, okay, and KSP is that. So the units will be mole to the power 3, dm to the power 9. Okay? Okay. Now, so KSP only applies to saturated solution or sparingly soluble salts. Okay, KSP is an equilibrium constant, so it changes only when temperature changes. It does not change with the amount of solid present. Okay, so it doesn't matter whether the amount of solid you have 1 gram present or 1 kilogram. Okay, as long as there's some solid present, that's you can get equilibrium. Alright? Okay, so try to do example 1.1. Okay. Can? Let's see. Done? Okay, now let's go and learn about calculations. Okay, now it seems to me sometimes students have a bit of a phobia about solubility and solubility product, which I don't quite get, because I personally think it is easier than the acids and bases stuff. Okay? Now, look at what numbers you are given. Okay? You are given the solubility of silver sulfide is 2.48 times 10 to the power of minus 15 mole per m3. That 2.48 times 10 to the power of minus 15 refers to the compound Ag2S. Okay? So, when you dissolve, you are going to produce 2 Ag plus and 1 S2 minus. Okay? So, since you produce 2 Ag plus, the concentration of the Ag plus, it should be 2 times 2.48 10 to the power minus 50. Okay, which is actually a very, very low concentration. And then the S2 minus is 2.48 times 10 to the power minus 50. So your KSP, okay, that is the expression. And then, because you produce 2 Ag plus, it should be Ag plus squared and S2 minus. Okay? So you substitute that value in, okay? And then you get 6.10 times 10 to the power minus 44. Okay? Unit, count the number of ions, and then there are 3 ions, so it's mole per dm cubed to the power 3. Okay, so mole cubed dm minus 9. Alright? Okay, so that is given solubility, calculate KSP, which is quite straightforward. Okay? Now let's look at the next one, where you are given the KSP, they ask you to calculate the solubility. So here the solubility is unknown. So you assign an unknown S or whatever letter you want. You write an equilibrium, you will get, for Pb2 plus you get S, for I minus you get 2S, because when PbI2 dissolves, it produces 2 iodide. Okay? So your KSP will be, expression is there. Okay, so you can get, in terms of S, you get 4S cubed equals to 1.39 times 10 to the power minus 8. Okay, you solve for S is 1.51 times 10 to the power minus 3. Okay, the solubility is 1.51 times 10 to the power minus 3 mole per dm cubed. So solubility unit is always going to be mole per dm cubed. Okay, where I see this is an issue for some of you, you all know how to use your calculator to take, let's say, if it's 10 to the power 5, instead of taking cube root, you take 1 to the power over 5. You know how to do that? The 5th root. There is a function on your calculator. Okay? Okay, done? Okay, let's go on to the next one. Okay, so are the values of KSP good indicators of the relative solubilities? Okay, so here you have barium carbonate, silver chloride, silver chromate, and calcium fluoride. Okay, so if you look at the ions, so one's in white, have the same number of ions. Okay? So, when it has the same number of ions, you can sort of tell whether something is more soluble based on the KSP. However, the problem arises when the number of ions are different. Okay, so you compare, for example, the barium carbonate and the silver chromate. Okay? It would appear from if you don't think about it carefully enough, then the silver chromate is not very soluble. Because from just judging from the KSP, because it's 1.1 times 10 to the power minus 12, whereas the barium carbonate is 5.0 times 10 to the minus 9. It is 3 orders of magnitude different. Okay, but when you actually calculate out the KS, the solubility, they are not very different. Okay. All right. So personally, you should only compare, use KSP to compare the solubilities when the number of ions are the same. If the number of ions are different, it can, lead you to a wrong conclusion. All right? Okay? Okay. Done? Okay, let's talk about the common ion effect. Now let's look at this equilibrium and consider a situation where you have either A or B in the solution. Okay? Now, when I say A and B, I mean A and B from a different source. For example, if I have silver chloride, I can add extra chloride by adding sodium chloride, which is very soluble. Okay? The result will be that precipitation will occur. Okay? Because the equilibrium will shift to the left. Okay? So, the solubility of the salt, okay, it would be lower than the solubility in water alone. And this is called the common ion effect. Okay? So let's look at the example and see, I think it will be clearer. Okay, so let's say you have silver chloride. They ask you to calculate the concentration or solubility in mole per dm cube, given the KSP. Okay? So in water, all of the silver comes from the dissolved silver chloride. Okay? So therefore, the concentration of the silver plus is equal to that of the chloride, which is equal to the solubility of the silver chloride in water. Okay? So that's the KSP. The solubility is 1.41 times 10 to the power minus 5. Alright? You all need to copy this now or not? Okay? Okay, noise means finish. Now, let's consider the next situation. Now, let's say instead of dissolving it in water, we dissolve it in sodium chloride, 0.1 mole per dm cube. Okay, now, you remember from Equilibria, here, the initial concentration of the chloride is not zero. This is what you need to realize. It is not zero. We have put in some chloride from another salt, which is sodium chloride, so it is 0.1 mole per dm cube. Okay? Therefore, when the silver chloride dissolves, okay, let's say it's Q, then the chloride is 0.1 plus Q. So KSP expression is that Q times bracket 0.1 plus Q. Okay. Here again you can make an assumption because Q is going to be very small, much smaller than 0.1. So because it's sparingly soluble, therefore you can and there's reduced solubility, Q is small, so you approximate it to 0.1. Okay? And therefore, that would be your answer. Okay? So, the solubility of silver chloride in 0.1 mole per dm cube is 2 times 10 to the power minus 9, as opposed to the previous question, the answer, where it's 1.41 times 10 to the power minus 5. So it is 4 orders of magnitude difference, which is 10,000 times. Now, if you think about, for those who have finished, if you think about it, there can be applications of this industrially. Okay, because silver is a precious metal. So, if you want to precipitate it out, okay, you can make use of this technique. Alright, you want to print. Okay, let's look at the next part. This is selective precipitation. Okay, so remember, this is where I asked you to remember about what KSP is. So KSP is the constant, okay, for a saturated solution at equilibrium. Okay, ionic product it is the same expression, however, it refers to the instantaneous concentration of ions at any given, for any given solution. Okay? So, the expression is the same. Okay? Now, however, the square bracket A and the square bracket B for the ionic product refers to the instantaneous concentration of any solution. Okay? For KSP, it refers to the concentration at equilibrium in the saturated solution. Alright? So, when is IP equal to KSP? At equilibrium, when the solution is saturated. Okay, so change in IP as the salt dissolves. Now, when you put salt in water, initially the ionic product is 0 if it's just pure water. You put the salt in, it dissolves, the ionic product will go up. Okay? Now, if the solution is unsaturated, that means you have only put a little bit of the salt in. The IP, the ionic product, is going to be lower than, the value of the IP is going to be lower than that of the KSP. I want you to think of KSP as a number, a value that cannot be exceeded. I want you to think of it as a maximum. For a particular temperature, that is, okay, when you calculate out the expression, it cannot exceed that number, otherwise it precipitates up. Think of it that way. Okay, so you add more salt, more dissolves, the IP increases. Okay, eventually you get a saturated solution. Okay? If you add some more, then no more salt will, once it reaches saturation, no more salt will dissolve. Okay, and eventually you can and will reach that point. Okay, there's a certain maximum. You can do this quite cheaply at home, even if you use sodium chloride. You can just keep adding salt to it in a glass of water. Eventually you will reach a point where no more of the sodium chloride will dissolve. Okay? Alright? So then you have a saturated solution with undissolved solute. And at that point, the ionic product and the KSP has reached the KSP value. Okay? Can. So the KSP represents a maximum. Okay? Okay. So, consider, okay, this is, you have two different solutions, you mix it, and, okay, what will happen? Now, if you, okay, I want you to think of something like this, which you probably have done in the lab. You have silver nitrate, you have, think of sodium chloride. Okay, both are solutions, but when you mix them together, a precipitate forms. Okay, so what's happening is this situation is occurring. Okay, when you mix them, the ionic product of the silver chloride exceeds that of the KSP of the silver chloride. Okay, so what will happen is that the silver chloride will start precipitating out. Okay, then the concentration of the silver ion and the concentration of the chloride ion will decrease as the takes place until you reach a point where the concentrations of both the ionic product decreases, right, until it reaches the KSB value. Okay, and then you have established equilibrium and you stop. So what you will then have is a saturated solution, saturated with silver ion, chloride ion, and with a silver chloride precipitate. Okay, I'm using this example because you should or you will have done it in the lab, and I honestly hope that you remember it. My 3 classes are, if you do not remember, today when you go home, go to YouTube and look it up. Okay? And the quieter I say things, the more threatening I am, right? Better do it, huh? Okay. Next. Now, IP less than KSP is not saturated, so no precipitate. IP equals to KSP is saturated, okay, but precipitation will not occur. IP greater than KSP is saturated and precipitation will occur. Okay? Now, okay, you prepare a solution by mixing 100 cm³ of calcium nitrate plus 100 cm³ of sodium fluoride. Predict precipitation will occur. Now, take note, the concentration is the same, the volume is the same. However, when you mix them together, the volume increases. It doubles. So, what happens to the concentration? This is something that you all need to figure out quickly. Because if they ask in MCQ, you need to do it fast. It should halve, right? Agreed? Double the volume, therefore concentration is half. Alright? Okay. So, the concentration of the calcium 2 plus should be equal to the concentration of the F minus and is half of the original concentration. Okay, so that is the equilibrium. Calculate the IP out. Take note there are 2 F minus, so it should be F minus squared. Okay, and then you get the IP as 1.25 times 10 to the power of minus 10, which is larger than that of the concentration for, the KSP for calcium fluoride. Okay, so since IP is larger than KSP, the precipitation of calcium fluoride will occur. Alright? Okay. Any questions so far? Okay, let's do a little bit more. Now, in year 1, you would have learned about separation methods. Okay? You can actually make use of the different solubilities of substances to separate them out. Alright? And sometimes it can be why we will go to this stage is because the substances that you may want to get out may be very precious. you will be thinking of things like gold, silver, and other precious metals. Okay? Interestingly enough, silver and lead, right? They are often found together in the same ores. So when they mine lead, often they will find silver also, but the silver will be much lower concentration. Okay? So in this case, okay, you can get chloride fairly easily because sodium chloride, common salt, okay, you can supply the chloride. Now, you can precipitate out the silver chloride first because the lead chloride is more soluble. Okay? Only when you increase the chloride concentration does the lead chloride start to precipitate out. Okay, so for example, you have a mixture, you have lead nitrate and silver nitrate, both same concentrate. Sorry, the silver is 100 times less concentrated than the lead. Okay, so you add chloride ions, determine which one will precipitate first, and at what concentration the chloride ions will precipitation occur. Okay, so less soluble salt precipitates first. Now, here it would be tempting for you to straight away use the KSB values. However, it would be wrong because the number of ions is not the same. Okay? So, you need to calculate it out. Alright? We have talked about this before. So, you need to go and calculate the chloride concentration for each and equilibrium for each salt to be precipitated out. Alright? Okay, so silver chloride. Now, the silver ion concentration here is fixed. What you need to find out is the chloride concentration. So 1.6 times 10 to the power minus 6. So the silver chloride will precipitate out when chloride concentration is greater than 1.6 times 10 to the power minus 6. Okay? So, for lead chloride, then calculate Y is 1 times 10 to the power minus 1, so it's 0.1 basically. So, lead chloride will only precipitate when chloride concentration exceeds 0.1 mole per meter cube. Okay, so silver chloride precipitates first. Okay, and when the chloride concentration is 1.6 times 10 to the power. Alright? Are there any questions so far?